Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And now he is a Stanford faculty member. It wasn't our choice, but it was a short period of time. It was his choice. Well, it wasn't his choice either, his department's choice. Okay. We're very happy to have him here, and he's going to be giving us a talk on ad auctions and algorithmic perspectives.
Yeah, thank you very much. Always great. That's why I keep coming back. So I'm gonna talk about ad auctions. I'm gonna, define what it is and how it works very quickly, and then I'll get into the particular problem that we are looking at. The main part of my talk is about the allocation problem, how the ad space should be allocated to advertisers. And I'll talk about the joint work that with Vijay and Umesh. Hopefully I will have time to talk about incentive compatibility issues also, and the joint work that I'm sure someone will give a separate talk here about these types of works, but I will mention them briefly. So how do they work? I can show you easily. If you go to Google and search on something, let's say Seattle. So this part is the result of search. It's decided based on the PageRank algorithm or other the web analysis algorithm that Google is using. But the sponsored links here and there, it's decided that, so it's the Google is selling its space using an auction. So what you do is that you go to Google and you say, I'm interested, if someone searched on Seattle travel, show my ad on the right side or over there, and I pay you this much. I pay you like 10 cents if someone clicks on my ad. So Google, based on some algorithm, decides which ads to pick and in which order to show. And then if the user goes and clicks on one of these links, Google will charge the company some amount of money. Yeah. So the range of this, the value of this click, it goes from a few cents, probably this Seattle travel is like a few cents, but it can be up to quite a few, like over $10 for certain keywords for which there were lawsuits, for example, Vioxx or other drugs for which there were some side effects, and lawyers were trying to collect yeah, then, well, you're making Google feature, so it's not exactly to. Right, so you can, yeah, we can do the same thing. So,
so this is what prevents Google from hiring a group?
well, we will get into that. Actually, as far as I know, Google is trying to avoid this. So what people do is that they click on their competitors to make them, to go out of business. So probably if you're, the company which your main source of revenue is this, you really want to keep it, healthy. But all right. So before I, so the question that Google or other search engines have is that once a search query arrived, which advertisements to pick and how much to charge the advertisers. And the main thing that I'm going to talk about is the first question. What is the best allocation algorithm? Before getting to that, let me just define a few jargons. So this what's cost per click and click-through. So the bid is usually called cost per click. The advertiser goes there and says, I pay you 5 cents or 20 cents or whatever if someone clicks on my ad. So advertiser goes and gives a list of keywords. Usually it's a long list of keywords plus a number, how much he's willing to pay. What the search engine computes or estimates is the click-through rate. What's the probability that the user clicks on a certain ad? Now, you can have different algorithms, and I know people are here who are like the experts in finding the best estimators. But you can assume that the search engine is interested in the expected value. What is the product of CPC and CTR? What's the expected revenue if I put this certain ad in this position if someone searches on such and such keyword? Another thing that advertiser specifies is the total budget. You don't want to get a bill of $100,000 tomorrow from Google. So you say, today I'm going to spend only this much on my advertisement. So that's, you can go to, I don't know how it is for MSN. In Google, you can go and set up a website and enter all this information. Probably it's now true for MSN too. So now the question is, when the search queries are arriving one by one, the search engine should pick up and show them. So this very simple mechanism has been extremely successful. The search engines, they made a revolution in information retrieval in the way we use the web 10 years ago. Right now, they are, the web experience is very much dependent on the quality of the search engines. We are really dependent on them. And this is probably the second revolution. They are revolutionizing the advertising. The size of this business is over $5 billion at the moment. Google, MSN, and Yahoo are the major players in this game. And it's helping many small businesses to thrive. Many small businesses are finding their customers. The good thing about this type of business is that you can really target the people who are interested in your product because they have just searched on a related keyword. And so it's expected to grow because the size of the advertising sector is about $200 to $300 billion a year, and this is like around $5 to $10 billion. So we expect to see, this type of advertising, this type of target advertising to be bigger in terms of dollars. And, it's to some extent helping user experience also. You might be benefited from the links. And moreover, it's paying for the good search results that we get every day. So for me, it's a very interesting object to study. There are several algorithmic and game theoretic questions that one can ask. I don't think the mechanisms that Google or Overture or MSN are using are optimal. There are several problems with them, and there are several ways to improve them. And I will talk about them. So I'll try to define an abstract problem. Please interrupt me anytime if you think this abstraction doesn't make sense or it doesn't fit reality. I'm assuming that I have n advertisers. I know their body through Bn, and I know the bits. Bij is bid of advertiser R, J. Now, I will say bid, but what I really mean is the expected revenue. It's like the CPC normalized by CTR. You might charge even, so some of the search engines don't charge the exact bid. They charge the next highest bid. But, for whatever query that arrives, you can look at your particular advertiser and say, if I show his ad, what is my expected revenue? You can compute that function, and let's call that bid. Let's call that Bij. So suppose you know those values too. Now the queries are arriving, and you want to allocate the queries to one of the advertisers. Now you saw in the Google's webpage that there are a few different slots. Let's say it's just one. It's quite easy to generalize it later. So that's my problem. And what is my objective?
You don't have all the numbers for why the Bij is expected revenue. Will not run out by expected revenue, but by absolute revenue.
It's true. So I'm assuming that it's happening at such a high rate that they expect, that it's, yeah. And I'm assuming, so it will be clear. Later, I assume that these Bij's are much smaller than Bi's. which makes sense. You know, your bids are usually of two order of magnitude smaller than your budgets. And then, you know, everything will work, you know, as the expectation. I don't think it will make a big difference if you change the analysis, but I just didn't get into it. So, all right. So, what is my objective? So,
Independent of the other players. So things like price or things like that do not exactly fall in this category because it depends.
So what do we mean by thin price? Is the next price or the next live price, right? So next bid that is still live. When a query arrives, I look at the bid right away. So I don't assume that I know it in advance. So I look at it in an online fashion, so it doesn't make a difference. And so that's the objective. You can look at different objectives, but I think it's not a very bad objective to look at. You want to maximize your revenue. And so what do I mean by that? You can have different algorithms, and for different instances, some of the algorithms might do better, some of them might do worse. How do you compare two algorithms with each other? What I look at is the competitive ratio, which is a natural, which is the main measure for comparing the performance of two online algorithms to each other. So what I do is that, you know, I let the algorithm run during the day. At the end of the day, you know, the algorithm has allocated some of the bids, you know, to some of the advertisers, and you know, so I look at the revenue of my algorithm. Then I see, now that I have all the information, I can compute what is the best thing that I could do. What's the best offline algorithm? I look at the ratio of the two. I'm looking for the algorithm with the best guarantee. The algorithm for which the revenue of my the algorithm for which the revenue over the best offline is as big as possible. And I call that the competitive ratio of my algorithm. So I will show you that the greedy is half competitive. What it means is that if you do allocate them greedily, your revenue is guaranteed to be half of the optimal value. And then I give you an algorithm which is 1 minus 1 over E competitive. Now this is 0.623, so it's like only 25% improvement, but it's optimal. Sir, yeah.
We don't have forecast for what the available supply of impressions are.
Yes, yeah. I'll get to this. I'll get to this later. Probably you have some information, but this is, you know, we are in a business where the rate of arrivals are quite unpredictable and dependent on real outside life, right? Whatever happens in the, you know, if there is a flooding, if there is, you know, some attack, people are looking for gas masks, all of these things can happen the rate at which you get the queries. So looking at it from the worst case point of view is not that bad.
So do you consider the situation when if you run your program, particular advertiser gets, you know, put it down, and this product doesn't get sold, then next time you come back and
Right. So what you're saying is, how does my allocation mechanism is changing the dynamics of the auction? I'll get to that. So yeah, please remind me to talk about this.
So I grant you that if the gas mask comes up because of September 11th, that's obviously slide. But the assumption that then the click-through rate is constant, as the click-through rate.
Yeah, click-through rate is constant, but I'm not assuming that. No, I'm not assuming.
Changes, then your bids change.
Sure. No, I'm assuming that at every moment there is a separate algorithm written by like Chris and Joshua who tells me like what is the click-through rate, and I normalize my bid at that time. I'm just so I talk about how I have it, but I say, let's say at any second I have it, and I'm not assuming that it's fixed all the time. You will see. So yeah. No, yeah, you can.
The revenue of what the algorithm in equilibrium to what the rev offline.
Yeah. No, so I'll get to the question of dynamics later. My algorithm is not truthful. You know, Google's algorithm is not truthful either. The thing about this algorithm is that you can have any charge mechanism. You can charge the people their bid. You can charge them the second highest bid, whatever you want. This is your allocation mechanism for that. Yes.
you look at 1 month, what's the capital of the problem, and then you expect that every day you get the pattern of queries?
No. No. Like, you have to have a lot of statistical information. Like, you can say, you know, maybe on Valentine's Day things change, but I take that into consideration. So you can have, like, try to build up a huge statistical database which can tell you the rates, which predict the rates for you, and then try to solve the...
How it predicts the click-through rate.
No, not the click-through rate, the arrival rates.
The arrival.
Right. Yeah, so definitely, like, you know, so that's another approach. I'm looking at this particular one where you are trying to optimize the worst case. All right, so let me first look at the greedy algorithm. So greedy algorithm is something that Google used to claim they are doing. They are not doing it anymore, and they are not claiming it anymore. But what they say is that we give the query to the advertiser with the highest bid. So we rank your queries. What they were claiming was that if you give a higher bid, you will end up in a better position. And, you know, you can outbid the rest of the people and get, so that was their claim. But now they have started to have this smoothing algorithm so that, you know, they spread your, so they are not doing this, but it's a good abstraction of what they are doing. So let me just show you with a quick example why it's not the perfect algorithm. Suppose you have two bidders. Bidder 1 is bidding $1 on books, $1 on CDs. Bidder 2, 99 cents on books and $0 on CDs. Let's say in the morning you get lots of queries about books, and in the afternoon you get lots of queries about the CDs. Now what will happen is that, so in the morning you get the 100 books. Bidder 1 is paying slightly more. You will fill his, almost fill his budget. Then when the CDs arrive, he's buying only one CD. So pretty much you're not using, because bidder 1 is bidding more for the books, you're allocating all the books to bidder 1 until he runs out of money. When the CDs are arriving, bidder 1 doesn't have any money, and bidder 2 is not interested. So your revenue is $100. Clearly the optimum is to give the books to bidder 2 and CDs to bidder 1, and then your revenue will be $199. So this example shows that your revenue could be as bad as half of the optimal. And one can prove that. It's a simple proof to show that greedy is half competitive. So this is as bad as it can get. No. So see, suppose I'm saying bid, right? But you can put here, this is the expected revenue, right? Based on the mechanism that you have and the click-through rate. If there was no budget, the greedy was the optimal. Yes.
So how much are you charging bidder 2 for the book click? You were charging bidder 1 the second price for the book.
Yeah, I'm not charging first price. I'm saying, you know, let's have some, yeah, I'm talking about allocation. Let's say I have some pricing mechanism. It could be the second.
What he wants to say, I think, is that he would have allocated all the books to bidder 1, and then when the CDs came around, you know, he would have been in trouble, you know.
But yes, so the concern is that if you charge the floor on both of those, you're going to make less money than the original case, right? So you have to, you're awarding the auction to the lower bidder, and you need to decide how to charge them.
It's like you have a bidder 3 that's going 88 cents on both.
Yeah, right.
You're making a kind of implicit assumption.
Yes, I'm not putting all those people there, but right. So you're asking about the question how, you know, changing the allocation, it might change the charging mechanism. Well, you know, Google is definitely doing something. They are not always putting the highest bid up there. They have some mechanism for charging. They can try that. Maybe when they don't always put the first bit up there. Maybe sometimes they put the second, they charge the third. So I'm assuming that your charging mechanism can take care of this.
But do you take into account the fact, this is just assuming that there's only one coming up, but there's a list of those. So, I mean, there's the whole list of those. Maybe the second one,
Yes, yes.
So this was the example to show that.
Yeah, this is really a toy example. There are many, many artificial things about this example, but it's really capturing the essence that greedy can beat you. Greedy can be suboptimum because you don't look at the speed at which advertisers are using their budget. They might run out of money pretty quickly early in the day, and then later when the queries arrive, there is nobody who is interested. So you have to allocate them to someone.
Yeah. A question, which was the question that everyone's been asking. Can you define what alpha is just by the allocation mechanism? So you say greedy is, well, any algorithm is alpha competitive, and figure out what alpha is. Does that make sense in the absence of the pricing? I mean, I think that's what you're asking.
Yes. So so I'm assuming something. Yeah. And that thing is that I know the expected revenue of a single bit. I know if I allocate. That's a function of my. That's a function of my pricing. Yeah.
But you see what you assume is that the price independent of the allocation.
No.
Yes, because otherwise it doesn't make sense to say you charge $1. Because maybe if you allocate this, the $1 becomes 50 cents.
No, I charge, right? My charging is not offline later in the future. When I allocate it,
in the real world, it's $1.99.
Right.
And you actually charge the 99 cents and not the $1.
Yeah.
But if
No.
Charge the $1. I think one thing that happened is your example.
I know. Yeah. Right. The example, there was something wrong.
Right, in the first example, you had price option, and the second example.
I'm sorry. This is that was confusing. No, the first one.
No, the first example, you had a second.
You're right. Yeah, this shouldn't be there. This should fill it up. Thank you. Oh, okay. Thank you. Yeah, I know. Yeah, I was confused myself, but I thought that maybe nobody notices. But anyway. But that was the source of confusion. But I have some time problem. I won't be able to.
Right, you can't fix the price.
No. I'm saying, there are some pricing mechanisms that won't have this property.
By the way, that will probably bother you about everything.
Fine. So you say there is a pricing scheme such that the price will not depend on the allocation, and then this is done.
Yes, I don't know what you exactly. Yeah, right. So what? No. Right. Suppose I charge.
I don't know any.
No. Let's say you charge.
I think second the actual second price option to do the charging as to do in the second price option will not fulfill the actual.
No, what do you mean by the second price? So if by the second price you mean the next live bit that I choose, right? So if I choose the 5th%, I charge the 6th highest. If I choose the 7%, I choose the 8th highest. Then it's the next highest, then it works. Why? You can do the same thing here.
No, you can't, because now the prices you charge will depend on the allocation. If somebody drops out, the price will change.
Yes. But when the query, no. So I talk about BIJs when the query arrives. So BIJ, a particular person, might depend on time. I talk about BIJ, so I ask the advertisers what their BIJ is when the query is there. This might change over the time. If you let me go, that my BIJ can. Let me go. Let me continue. All right. So where was I? All right. So
this we will not do online. This we're going to do talk.
No. We can do. No. Once I explain my algorithm, it will be.
Get like 1 minus 1 over e of the talk.
Yeah. Exactly.
Or half.
No, I think once I explain my algorithm, it will be clear. But if it's not clear, we can continue after the talk.
Right.
All right. So I told you that greedy is half competitive. And now I want to improve it to 1 minus 1 over e. Let me mention two known results. So 1 minus 1 over e competitive algorithms were known for special cases of this problem. And the special cases, for example, when the bids are 0 or 1 and budgets are 1. So you have $1, and when a good arrives, you either say interested or not interested. And if you're interested, you pay 1, otherwise you're not, your bid is 0. Then it reduces to online bipartite matching. Karp, Vazirani, and Vazirani 90 gave a 1 minus 1 over e algorithm for this problem. Kalayasundaram and Pruz in 96 and 2000 looked at a different special case, which is the online B matching, where your bids are, again, you are interested or not interested. If you're interested, you're bidding epsilon, and your budget is equal to 1. So again, they don't allow different bids.
What is B matching?
So it's just the matching in which you can be matched to B people.
I see. Okay.
So B here is 1 over epsilon.
So it's bipartite instead of bi.
No, it's bipartite, but you can be matched to B people. Yes.
Okay.
Yeah. So there again, they gave a 1 minus 1 over e algorithm. So their algorithm is deterministic, and I will discuss their algorithm in details because I will use their idea very, very crucially. So our result works for arbitrary bits. We are not just looking at this case where the bits are either 0 or 1 or 0 or epsilon. We have this assumption that the bid over budget ratio is very small. And I want to argue that it's a mild assumption in this context because your bids are usually much smaller than your budgets. And for giving this, we are introducing this new technique, tradeoff-revealing LP. I'll talk about this more.
What's LP?
Linear program. That's a question, right? All right, so let me explain the KP algorithm, the Kalayasundaram and Pruz. So what they say is, the natural thing. What was the problem with the greedy algorithm? It was running using the budgets, of the one bidder quite fast. So they say when a query arrived, among all the people who are interested and who have some budget, give it to the person, to the bidder, with the highest remaining money. So here, the bid, so it's either interested or not interested, right? You're either bidding epsilon or 0. So the query arrives. There are a few people who are bidding epsilon. You give it to the person who has the highest remaining budget. And it's clear for this example that you will do better because when the 100 books arrive, you divide it 50-50 between the two bidders. The CDs arrive, you give it to the first person, so your revenue is 1.5, optimum is 2. So you're doing better. This example is like 75%, but I can create a more complicated example in which the revenue is like 1 minus 1 over 8. And they have a very elegant combinatorial proof for this. But the difficulty in designing algorithm in our context is that you have these two criteria, bids and budgets, right? So you cannot say give it to the person with the highest remaining budget because he might be bidding much lower. You might have two advertisers. One is bidding higher, the other one has higher budget. You have to make a decision between these two criteria. You really need a trade-off curve. The question is, what is the best trade-off curve? And that's the best trade-off curve. That's what we prove is the optimum trade-off curve. Where psi of, alpha is the fraction of money that you have spent so far. Psi of alpha is like this function, 1 minus e to the power of, and it says that when a query arrived, look at the bid of the advertisers, look at the fraction of budget they have spent, compute the psi of that, and normalize the bids by that function. And give it to the person who has the highest normalized bid.
Here you make the assumption that the bid is always constantly change. But if I were advertise, I would like to have my bid higher beginning. And once you approach the budget, almost budget is gone, I would like to reduce my bid.
So you're saying you go inside during the run, during the day, you go and change your bid, right? Yeah, so I'm assuming that I have the bids for this certain period of time, like this day. I don't know, again, for Microsoft, for Google, once you change your bid, it takes quite some time to reflect there, right? It's not, No, it's not 15 minutes anymore. Like you have these three stages where you are, you know, the. The same budget. I think so. Maybe I don't want to control. You know a lot about these things, but I thought that it takes a lot more time until. What I heard was that you go through a few stages and it takes some time until it happens. But the other answer to your question is that this algorithm is doing exactly this.
Oh.
Because it's reducing your bid. Yeah.
Okay, so that's
And it's doing it
Yeah.
in an optimal way.
Yeah.
this is actually
Changing the budget, then if I were to change the budget on a Bitcoin over the course of the day, then I could game the system.
Right. So no, this is I'm designing, I'm analyzing the algorithm, assuming that everything, the bids and budgets are offline. I don't think you can gain it much if you can gain my features.
What he's going to do is he's going to what he's going to do is he's going to just put a little bit of the budget in. Okay.
No, it's always good for you to have a lot of budget.
Competitors have run out.
No, it's always good for you to have a lot of budget. So later I will discuss this. Eventually, if people start, understanding what's going on, so they will try to put a lot of budget. They will commit to a lot of budget, so then your algorithm becomes like greedy. So this algorithm, if your budgets are like infinity, then it becomes greedy algorithm. If your budgets are limited and the bids are almost equal, then it becomes like the KP algorithm.
Even if your budget's infinite, the size is going to be finite. Yes.
So, all right, so.
Because it's a fraction of your budget.
Do you want my input in this conversation? Or if it's going to go right, then I don't say. All right, so, yeah. Yeah. Right, so it's simple. So you got it already. When a new query comes, if it was the greedy algorithm, if B2 was greater than B1, then advertiser 2 would get it. But in this new algorithm, B2, if it's slightly bigger than B1, it doesn't suffice anymore. The ratio of B2 over B1 should be this psi of alpha 1 over psi of alpha 2, so it's slightly more. Like you have to pay 10% more if you are at the end of, you're using your, you're running your out of budget quite quickly. All right, so I put that psi function, that blah function, so where did it come from? And so in the time that I have, I will try to give you an idea of how we derive that function and how we prove that that's the optimal function. So how did we do it? First, we looked at the KP algorithm for a very long time. And then we gave a new proof for its analysis. We gave a linear programming-based proof. So we managed to write a linear programming which describes the worst-case instance for this KP algorithm. And that's called factor-revealing LP. And I will, this idea is used in other contexts as well. I will talk about them later. And then this is this was used in many different instances. What we did was that we looked at the dual of that factor-revealing LP, and the dual of that linear programming told us how to come up with this trade-off function. So here, the linear programming helped us to design a better algorithm. And that's like the advancement technically over the previous algorithms. The previous algorithms, the linear programming were used only for analysis. So let me first talk about this new proof by KP. So I have this parameter k, which is my discretization. Let's say it's large enough. Then define x1 to be, so when I have this discrimination parameter, I can classify my bidders. I can say these are the bidders who have used 1 over k of their budgets. These are the bidders who have used 2 over k all the way to k over k of their budgets. Then if I have this xi, says that's the number of such bidders, then my revenue is roughly, assume that all the budgets are 1. For the sake of it doesn't make a difference for my analysis. So then my revenue would be sigma xii over k. let's say optimum can exhaust everybody's budget also. That's also an assumption without loss of generality. So I know my revenue is this much. I want to bound X size. I want to say like X1 cannot be too big. How do I say it? It's a proof by picture. So it's clear that these are my advertisers. X1 of them have spent 1 over K, X2 of them 2 over K. And so what is the revenue? The revenue is the painted area. And the optimum can exhaust everybody's budget. So the optimum is N, the area of the whole rectangle. And my question is, how small could this painted area be? Well, let's look at X1. How big could X1 be? Now, it would be very bad if X1 was very big, right? So can it be very big? Well, you're saying, this is my X1. I say that the optimum allocation managed to exhaust the budget of these people, right? I assume that optimum can use everybody's budget. So some queries arrived, and optimum allocated it to these people, but the KP decided to give it to some other people. It couldn't be that the KP didn't give it to anyone at all, because there was some person who had spent only a little bit of his budget and he was interested. And moreover, the algorithm wouldn't give it to anyone who had spent a lot more of their budget. So all of these queries, when they arrived, they ended up like low, right, to the people who had spent very small fraction of their budgets. So if I look at it, so it will boil down to that this area is equal to that, because all these queries ended up somewhere low here. So it's at least as big as that.
But I don't understand the picture with the optimal allocation. You see that optimum allocation, the width would be 0 for X1, right? So X1 is the number of folks who...
Yeah, I defined X1, X2 through Xk for the result of the KP algorithm, right? So let's say I run the KP algorithm, and that's the figure that I got. Now I say, look at these people that I couldn't give a lot of queries to them. I know optimal could, so there were some queries that arrived, but I gave them to some other people. Now I didn't allocate them to people who had spent a lot of their budgets. So I put them like down here. I could put them in this area at most. So I can write it. So X1 would be N over K. Once you write it, that would be the inequality that you get. We can do it again. You can look at this area, and you can say it can be put here, and that will give another inequality. In general, you will have an inequality like that, a linear inequality. All right, so let's put now everything together. You want to know how small your revenue can be, such that these inequalities that I told you, that I proved to you by picture, are true. You know that sigma x3 is equal to n. You get a linear program. That linear program is describing the worst case instance for your algorithm. The solution of this linear program is actually the competitive factor of your online algorithm. This is the thing that the idea that was used for improving the approximation algorithm for the facility location problem with Kamal and Mohammed. Later it was used for analyzing other online algorithms. This technique has been used also for computing the rate of a certain code in coding theory. So fortunately, we are lucky here, and we can solve this linear program exactly. We can solve the primal and the dual, so we can introduce the primal and dual and prove that that's the solution of the linear program. Once you try the instance that is suggesting, you will see that that works. So you can prove that the factor of the algorithm, the competitive factor of the algorithm, is 1 minus 1 over. All right, so far. Now, I have this new proof, this linear programming-based proof for the KP algorithm. Now, I want to find a way to modify it for arbitrary bits. And so the question is, where did this psi function come from? All right, so we talked about this. I don't need the reminder. So in the algorithm in our algorithm, the bit arbitrary, unlike KP, and we have this psi function, this trade-off function, which tells us how to allocate the queries.
So since they had just looked at all the bids being the same. Basically, they landed up looking at the psi function, just not scaled by the bid.
Yes, like the very flat, you know.
Right, so they looked at psi. I mean, you could describe their algorithm as that,
Yes.
with the bid not in there.
Yeah, so it's a common generalization of greedy and KP for appropriate choice of budget and bid. Yeah. All right. So the question is, for this algorithm, can we mimic the proof of that we gave for the Kalaga-Sundaram and Proofs algorithm? Well, now the problem becomes more complicated. Why? Because it's not clear that all the queries that arrived here, they ended up down there. Because this guy might be paying, you know, might be bidding delta, and the optimum decided to give it to this person, but someone else had used much more of his budget, but he is paying much higher. So epsilon is much, much bigger than delta. Actually, epsilon is bigger than this fraction defined by this ratio defined by the psi function times delta. So now when you write it, you know, something is missing, you know, so some of the queries are stolen by the, from this smaller, you know, from these lower slices to the bigger slices. And you want to somehow keep track of that. How do you do this? Well, you know, you have to, so after some inspection, it's, you know, and it's not very difficult to see, is that when these things happen, it's like you look at the right-hand side of your linear program, and some values from the right-hand side of one of the inequalities is deducted and some value added somewhere else. When one of these queries are being stolen from one place to another place, it's like, so it's like when one query is stolen from, you know, delta to epsilon, you look at the corresponding inequalities and you have plus delta here and minus epsilon here. So considering all the queries, you will get the same linear programming plus this delta function. And that delta function is a function of psi, your trade-off that you come up with, and the instance that you will have, right? So different queries will, you know, based on your psi. So whatever psi you come up with, I'll come up with different instances, and then we solve this linear program, and the solution of this linear program would be a bound for the competitive factor of my algorithm. The question is, can I come up with a good psi so that whatever pi you come up with, I will get still that same 1 minus 1 over e. So what I have to analyze, to make it short, is to find a way to know how the change in the right-hand side of my linear program will affect the value of my objective function. Well, there is a technique in linear programming for that. It's called, yeah, I forgot to say, but anyway. There is a technique for that, and that's called sensitivity analysis. But sensitivity analysis is for a very small deltas. So what's the idea there? It says, you know, suppose you have this linear program, and let's just look at the black. And that's its dual. Now, you add a very small number to the right, or a very small vector to the right-hand side of your linear program. You want to know how much it's changing the value of your primal program. What you can do is that you can look at the dual, and once you write the dual, you will see that the delta is appearing in the objective function. So if the change is very small, the value of the value of the optimum dual, the y star, does not change much. It's like you have a linear program, you change the objective function very slightly. Your solution still remains the same. The same y star will be optimum. Yes? No, it's a constant. I'm treating it as a constant, yeah. It's actually, if I want to write it, it will be very funny. It will be very complicated. But I'm giving only the intuition here. So
in your actual proof, you don't treat it as a constant?
No. In the actual proof, actually, I don't have to talk about any of this. I just plug it in and it works. Right? It's like in the linear programming, suppose
find a solution
and you plug it in the inequalities and it works, right? But I'm telling you how I drive that. So, all right. So what was I saying? Yeah. So if this delta was small, then I could just look at the dual, like this delta times y star. If y star is the optimum dual, would exactly tell me that how much the objective function is changing, how much the factor of my algorithm is changing. But the delta is not necessarily a small. Here, delta could be quite big, and the question is, how much does y star change when you introduce this to your objective function? So how much does the factor change? Well, we are lucky. So we can prove no matter what psi we choose, optimum dual remains y star. The solution of this linear programming is this linear programming has very nice structures. It's actually self-dual. And it can tolerate a lot of changes in the objective function. So I can change the objective function, still the dual solution remains y star. So I know that the change in optimum is still delta of psi and pi times y star. Once I know that, then I want to find psi as a function of y star optimum dual in such a way that no matter how, no matter what instance comes up, the change in the optimum is always non-negative. And that's the function that I have to plug in. It's like some of the values of the dual. Yeah.
You definition of delta. You need to define it in a way that's independent of any sense, right?
What do you mean?
Because you said it's a constant, it's not a value. It's not a function of x.
It's not a function of no, I don't, right, so I don't write the function as a function of pi, right?
Could you remind me what the definition is?
The definition of which? So based on whatever instance that you get and whatever psi function that you have, once you run the algorithm, you will see how the right-hand side of your linear program is changing. Right? Now this delta has a lot of properties. If I just, write it as a closed form here, it will be completely, it will be very messy. But there are lots of details that I'm not sure. So I don't know. Yeah, I don't know how to know. But what do you mean by a constant? So
Yeah.
it's not, yeah, right? So
It's not, right?
no, it's not a constant.
It doesn't depend on the solution.
No. Yeah, so I'll plug the...
But x also depends on pi.
X also depends on what? Yeah, sure. No, if it was a full function of both of them, a verified function of both of them, then this problem would be intractable. At least I couldn't solve it. This has a very nice structure, and that's why we can solve it. So it will be only a function of the, the... No. Eventually you will get that trade-off function, and that trade-off function works for everything.
I think we don't understand the definition of this.
Well, it's because I'm not defining it properly.
If I wanted to define it properly, not that I want, but what would you do? Tell us what you do. You would look at the linear, you don't have to go through all the algebra. Tell us what you do.
Yeah, so if I want to define delta general, so, I can take this pi off and say it's the delta of the psi, right? But then depending on different instances, I might get different things, right? Now, I can introduce a nice bound here and show that it's always the same. Then so it will be eventually I can bound it independent of pi. But I'm putting it as a function of psi and pi to make my definition well defined, to have a well defined definition here. Because based on your instances, you will, based on who is stealing from whom, you will get, different right-hand side.
Do you tell me that pi is a function of x?
No. Pi is your instance, right? I'm writing this, I'm putting all the parameters here, but at the end it doesn't matter anyway. All right.
Of course, it also doesn't matter anyway, not really, not necessarily do sensitivity analysis. You could just say, take KP, take greedy. Looking at the two of them, I guess that if I scale the KP answer by the bid, it is going to be a solution, and then I plug it in, or that doesn't work.
I didn't understand it. Yeah.
I'm saying, can you just, one way or another, pull the solution out of the air and just verify?
Yes. So.
Do you need delta to verify it? Or
No. Eventually, this is very, rough intuition of how you drive the function. Once you drive the function, everything is easy. You just plug it in and it works. And, so the good thing, so the rough intuition is that eventually this doesn't depend on pi. You can bound it by pi. You can say for any pi, I can bound this as a function of psi only.
Could also be, look, in KP they have equal bids. Here you don't have equal bids. How much would you expect it to change by for what it uses as the effective thing? Well, you'd expect it to change by the value of the bid. So I do that, I plug it in, lo and behold, it satisfies me.
No, but there wasn't the e to the power.
No, but I'm saying that you scale that function by bid.
No, the fact that you scale it by the bid, that's easy. But what is the function itself? That's the question.
I see. But didn't they already get that function?
No, that's actually the contribution.
Oh.
Yeah, so. All right.
So that function, so that was your question, was that.
That e to the minus, yes.
1 minus alpha.
Yeah, and it comes from here. Yeah, so, yeah, you have to, it's like a few pages of calculation. But I'm trying to give, all right. So, well, let's take my word that there is a way to choose psi that objective function does not decrease. Then, based on that, you get the corollary that the competitive factor remains minus 1 over e. And so in the KVV paper, there is a proof that 1 minus 1 over e is the optimum algorithm, regardless of whether you use a randomized or deterministic algorithm. But they don't have this assumption that the bid over budget is very small. That might change, so that might, so still you can,
Your algorithm is deterministic, right?
Yes, yeah.
So is there a way of seeing the fact that psi is an exponential function of
yeah, so this function could have it's a very natural looking function, and it might have connections with this but yeah, I don't know. We have thought about it if there is any simpler way to see this function, but yeah, we don't know. Yeah. So even for the case where the bid over budget is very small, we can show that the competitive factor cannot be improved to 1 minus 1 over e using a similar type of argument.
And if the bid over budget is large, do you know that you cannot do, do you get any result in this case when the bid over budget?
Yeah, so when the bid budget is large, not too small, then the problem is NP-hard, even the offline case. And the best approximation algorithm known is 1 minus 1 over e. But now, it might be that it's both on, you can have an algorithm online and approximation and gets the same factor of 1 minus 1 over e. So let me give you this algorithm, and I suspect that this algorithm will work even when the ratio of bids and budgets are small, but we don't have a proof yet. It might be just because we got lost in the calculation. So I don't see any fundamental way of. Okay, so let me quickly go over the KVV algorithm, the Karp-Vazirani algorithm. So in their algorithm, they looked at this, well, not very capital, they looked at this more romantic setting of girls and boys. So you have a set of girls, and the boys are arriving one by one, and you want to match them to girls. When the boy arrives, some of the girls say they...
I mean, the KP is kind of a totally promiscuous algorithm.
I knew you would say that. Actually, I knew from like a week ago that.
bipartite example.
Yeah. So, all right, so when the boy arrives, the girls say if they are interested in him, and you can match one of the girls to the boys, to one of the boys. You cannot change your match. It's an online algorithm. So what the algorithm that they are suggesting is that permute the girls randomly. So choose a random permutation of the girls, then the boys arrive one by one. When the boy arrives, look at the girls who are interested in him, and match the one who has the highest rank to that boy. So here, this girl is interested in, she's higher, you match that girl. So this girl cannot be matched to any other boy, and because this matching cannot be changed. The next boy arrives, nobody was interested. The next boy arrives, so these are the girls who are interested, so if you match it to this one. And you keep going like that, and they showed that the competitive factor of their algorithm is 1 minus 1 over e. And that's actually very nice proof. This algorithm, 1 minus 1 over e. Yeah. And so the question is, now in our context, yeah, optimum assigns, like up to the offline thing. You look at the maximum matching in your graph.
What is your cost function? That's the number of assigned edges.
Yes. Yeah, that's my profit function, yeah. So now in our context will be whether there is a trade-off between bid and rank. And the answer is yes. And the same thing seems to be working. So it works when the bid and budget are, the ratio of bid over budget is small. It might work even in the other case. I just don't know the proof. Oh, I forgot to, yeah. All right, so I guess we discussed this. You can change this algorithm to work on more realistic assumptions when you normalize by click-through rate, when you charge the next highest bid, when you assign the query to more than one advertiser. That was the question that I got much earlier. When you have some statistical information about the queries, can you use them? Now the question is, what assumptions do you have about your statistical information? If you want to make very strong assumptions, then the problem becomes easy. Like if you assume that there are some Poissons, then you know the rates. And it's mathematically uninteresting. I don't think it's very practical too, but the question is whether there are some minimal statistical informations that you can make and then solve the problem. And I had this question also. All right. So do I have time or not really? 5 minutes?
Yeah, like 10 minutes.
10 minutes. All right. So let me go quickly over the issue of incentive compatibility. So maybe after this. Yeah, no. Actually, when I'm done with the talk, then maybe the people who want to leave will. So it's easier. So, okay. So it's a business. I told you it's like a few $1 million business. So the bidders will do whatever they can to game the system if they can improve their revenue. Some of the mechanisms that they use is bid jamming. Bid jamming is that when you make your bid exactly like slightly less than the next highest bid, so that your competitor runs out of budget faster, so you will end up higher. The fraudulent clicks is that you go and you click on your competitor's ad until it runs out of budget. And this is not really a fraudulent thing. Sometimes it's better to aim lower positions. You will get less clicks, but some people tend to believe that you will get clicks from more serious advertisers, more serious customers. Because if you go down the list, like in the 5th in the list, that you're interested. Like if you're up in the list, maybe the guy was just lazy, know what he was doing and clicked on it. So, but all of this shows that you have to strategize, you have to think, you have to start getting some data, and
get people who have more time than money. It's not necessarily what you want.
Yeah, right. So it's there are now companies.
Position 1 or higher than anything else. I can tell you that.
I'm sorry?
Conversion rates on sales for paid search is highest in position 1.
Really? I see. Yeah, so some people, there are these news groups, some people claim that they would like to be second or third. Or. I see. Wow.
Pretty much, yeah.
Conversion per all text?
I'm sorry?
Conversion when you search it divided by click?
Yeah.
I will preach this to All right, but there are companies who, for different reasons, and I will get to that also, who give consulting on how to bid on Google, or and there are actually becoming quite a few. It's because people don't know, or they are not certain whether what they are doing is the best. So it's natural to ask whether you can come up with incentive-compatible mechanisms in which the best strategy for everybody is to be truthful about the bids and even possibly the budgets. Well, these types of auctions are, not very easy to make. One problem is because of the online nature of the auction. This is an auction in which you have these goods that arrive at unpredictable rate, and they should be allocated immediately. Like these goods that's immediately perishable. You have to sell it right away. And the other thing is that the bidders are budget constrained. These two things make the question of mechanism design or auction design more difficult. So we have looked at a few abstractions. Let's consider only budget constraint bidders. Let's say if you can design mechanisms for them. Let's ignore the online issue. Well, we did this with Christian, Jennifer, Nicole, and Mohammed, and we showed that even in the offline case, it's easy to observe that in the offline case, like the VCG mechanism is not truthful, mainly because the utility function of the bidders is not linear in money. They have a cap. Whatever clicks to them, if their budget is $100, you cannot charge them $150. Then under some assumptions, we show that designing truthful auctions is impossible if you want to allocate all the goods. And if you don't want to do that, we can design optimum auction. So there is other question whether you can design auctions for goods with unknown supply. It's work in progress, also slowly. And hopefully Mohammed will write whatever we have, and then I can make sure that. So there are some other works, very recent works, like in the last few months. So since the Google's payment mechanism is not truthful, so you have to look at the Nash equilibria. And people have studied, these two papers have studied Nash equilibria of the Google's payment mechanism.
So wait, can they do this exactly with sort of pay this and you charge always the next highest and therefore can calculate what the maximum or does it matter?
No, they do, so one of the papers, the Agarwal, Goel, and Motwani paper, prove a revenue equivalence theorem. They say that if you make the charging mechanism